Um, so welcome to Saturday Morning Astrophysics at Purdue. Thank you for joining us today. My name is Mariana Aguilar. I'm going to be the host for today. So I'm a first-year graduate student at Purdue. I'm in the Earth, Atmospheric, and Planetary Sciences department. And so when I was your age, I was a part of SMAP as a young student. And so SMAP is one of the reasons I decided to get into the field I'm in today. Because of SMAP, I now study how life can begin on icy worlds. So I'm a first-year graduate student studying that. But today we're going to learn something new and exciting known as chemistry in space. So that's what we're going to be focusing on today. Dr. Van 't Hoff, I'll hand it over to you then.
Thank you. All right. Hi, everyone. I am so happy that you're all able to join us today. So I'll start with a little bit about myself. So I'm from the Netherlands. I was born in the northern part, but I moved all the way to the other side of the country to go to college, which at the time felt really far, which is funny looking back because the Netherlands is actually smaller than the state of Indiana. So yeah. Growing up, I was always fascinated by astronomy. We live in the countryside with pretty dark skies, and I really enjoyed using my dad's small telescope to look at the sky. In high school, I realized that astronomy also involved quite a bit of physics, and physics wasn't my best or even like my most favorite subject. So going to college, I decided to major in something more biology and chemistry related. But I always had this voice in my head that kept saying, like, what about astronomy? So I ended up doing a double degree, and during my master's, I had the opportunity to do a research project with an amazing professor, Ewien van Dishoek, on astrochemistry. And I didn't even know that this field existed until I started that project. And for me, it really was a perfect way to combine astronomy and chemistry. So I obtained a PhD studying the chemistry during planet formation. And after that, I moved to the University of Michigan to work as a postdoctoral researcher for a couple of years. And this August, I joined the faculty here at Purdue in the physics and astronomy department. So I've lived here now for about half a year with my husband and our two cats. And just as a fun fact, when we got our cats, my husband ran an Instagram account for them. And before we stopped, we had about 100,000 followers. So, but this is going to be the only cute cat picture that I'm going to show you today because we're going to focus on water. So we're going to talk about the origin of water on Earth. And maybe that's the water that you, just like me, I'm drinking right now. And as Mariana said, you will get the opportunity to work with some real observations of water in space, which is the same observations that I have used in my own research. So during the talk, feel free to raise your hand if you have any question or put it in the chat. We'll monitor that and we'll try to answer everything that you want to know. Sounds good? Okay. So you already discussed with Mariana that about 70% of Earth's surface is covered by water, but that it only makes up about 0.02% of Earth's mass. So to get maybe a better picture of like what this small number means, this is what it would look like if we were to put all of Earth's water into a sphere. So this shows you how dry Earth actually is, even though it seems pretty wet. So we know that there can be liquid water on Earth because we are just the right distance from the sun. Not too close, not too far, just perfect. But where does our water come from? And why is Earth not completely dry? So why is there this little bit of water? And to give a little bit of a spoiler, we don't fully know the answer to this question. And in fact, there was this paper. So 2 months ago, this group of astronomers published a research paper, and they started their abstract stating that the origin of water, particularly on Earth, is still a matter of heated debate. So, and this heated debate, it means that there's different groups of people that have different theories about how Earth got its water, and they all have evidence supporting that theory, but there's no general consensus in the astronomy community about what actually happened or how much each of the different theories maybe contributed. And these authors, like 2 months ago, even explored a new theory. So what we're talking about today is really a topic of active research, and it's still evolving. So in order to address the question why there's water on Earth, where it comes from, we have to answer two other questions. So how do planets form, and how can we observe water in space? Let's start with the first question. How do planets form? So who can tell me what we're seeing in this image? You can put it in the chat or you can unmute. Yes, the Milky Way, that's correct. We're seeing our own galaxy. Because our galaxy is a thin disk, we're seeing way more stars when we look towards the center along the plane, and that's what we're seeing as this bright band when we have a very dark sky. But for this story, we're not interested in the stars, but we're actually interested in these dark regions. Does anyone know why some of these regions are dark? Yes, this is actually because of interstellar dust and gas. These dark regions are giant clouds of gas and dust that block the light of the stars that are behind them, making it look like there are much fewer stars in these regions, but it's just their light is being blocked. And we're interested in these regions because in these clouds, stars and planets are being born. So I'm going to show you a real computer simulation of how we think stars are forming in such a giant cloud. Okay, there it goes. Good. So we're starting with a spherical cloud, but because the material is not completely homogeneously distributed, regions with slightly more material will start to attract even more material because of their slightly higher gravity. And in this simulation, the brighter the color, so the more yellow or white, the higher the density, so the more material in a certain volume. And we can see all these filamentary-like structures forming. And now we're changing the color scale so we can really focus on the densest regions, because that's where stars are going to be born. So you can see it from all directions, and we're going to zoom in. And here in the top right, you can see material spiraling inward until the density becomes so high that we form stars. And those are those little circles moving around. And you can see more stars forming in other regions, and everything is moving around. And if you look really careful, you can see that that infalling material spirals and forms a disk around the young star. So you can see especially well here. I'm going to pause. This may be a difficult question, but if anybody has an idea why we form a disk? Somebody says gravity. Yes, it has to do with gravity. Gravity makes the material fall inward. So the reason that we form a disk is because we have to, yes, conserve angular momentum. So the material in the cloud moves around, has angular momentum, and one of the laws of physics says that it has to be conserved. This is the same principle as when you make a pizza and you start with a ball of dough and you start spinning it on your finger. Maybe you have those Italian chef skills, but then that ball of dough will form a flat disk, will form a pizza. So it's the same principle why we form a disk around a forming star. So this disk is actually really important because this is where the planets will form. So initially, the dust particles in the disk are smaller than sand grains. But when they collide, they can stick together, they can grow into pebbles, then boulders, and eventually rocky planets like Earth. And if they go even bigger, their gravity becomes strong enough that it can also attract the gas. And then we end up with a giant gas planet like Jupiter. So in this movie, you can see in the disk these dark rings forming. And that's because the forming planets accrete all the material in their orbit until it's all gone, and we end up with a planetary system. So to summarize what we talked about so far, when a dense region in a giant cloud of gas and dust collapses, we form a young star surrounded by a disk. And in this disk, we form the planets, and in about maybe 10 million years, we end up with a planetary system like our own solar system. And before we move on, is there anybody who wants to ask a question about this? Yes, Nathan.
Would it be possible to predict that a planet could develop life or could develop the ability to harbor life? I have the right conditions based on the formation pattern of a planet?
That is a really good question. And that is actually one of the questions that drives my research. because we were trying to find out indeed what the conditions look like and how we make planets. What do we need for life to form, and trying to connect all those things together that, yeah, maybe, hopefully at some point we can predict when and where we can form planets and whether they have life. So yes. We're gonna go to our second question, how to observe water in space. And for that, we're gonna watch a demonstration given by Alexi and Charles. So I'm gonna hand it over to you guys in the lab, and I'll see you back in a minute.
So I've got some tools here today. We've got 3 boxes that pass an electric current through a tube of gas. So we've got these 3 tubes of elemental gases. And we also have what's called a diffraction grating. So a diffraction grating, it's a fairly fancy film-like material, but essentially what it does is it splits up light into its components. Similar to a prism. If you've ever seen a prism make a rainbow, or even raindrops can do this outside, it's exactly the same idea as that, just in a slightly larger and more regulated scale. So we have a diffraction grating that splits light up into its parts. We have an electric current box, show you, that passes the electric current through our elemental gas and makes it light up. All right, so being the good scientists that we are, first I want to make a hypothesis about what's going to happen when I put the diffraction grating in front of the illuminated elemental gas. Does anyone have any ideas what will happen?
Naomi said that you should see the element's emission spectrum.
Excellent, very, very good. Maybe so we're going to illuminate our hydrogen gas. This is pure elemental hydrogen. It's the most common element in the universe. Okay, so hopefully we can all see the light passing through our diffraction grating from this illuminated hydrogen. And as suggested by one of our students, we do in fact see it split up into some lines. Importantly, you'll notice that these are specific lines rather than, say, a rainbow. Why do we see specific lines instead of the full rainbow?
Naomi said it depends on the specific wavelengths absorbed by the element.
Yes, very good, very, very good. So we have, in hydrogen, we have just the one electron, and this electron can move between energy levels, and when it does so, it emits very specific wavelengths of light. We call this the emission spectrum. So what we are seeing is the emission from this electron jumping around. This very specific emission acts kind of like a fingerprint for the element. So here we can see the emission spectrum, which is like a fingerprint for hydrogen gas. And if we were to point this at, say, a distant star and see these very specific emission lines, we could say for sure that there's hydrogen there. All right, we're going to move on to our next element. Our next element is helium. So we have helium illuminated here, the second most abundant element in the universe. And before we slide the diffraction grating in front, I want to ask, what do we think will be different about the emission spectrum from helium as opposed to hydrogen, and why?
So Naomi says more yellow wavelengths because the light appears more yellow and orange.
Okay.
We also have other hypotheses of it would have more lines, and also it would be less blue.
Okay, great. These are all great ideas. Let's see what hypotheses are supported by our data. So here we see the emission spectrum for helium. Notice, first of all, that it is in fact different from hydrogen, and many of the hypotheses you suggested appear supported by this data. Does anyone want to suggest why we see more emission lines?
Alvina says it has more electrons, and Matthew says it has 2 electrons instead of 1.
Excellent. These are both correct answers. Very, very good. So it has more electrons, so there's more electrons to jump around and be excited and emit more lines to make this new fingerprint. The astronomer like Dr. Hoff points her telescope at a distant star and sees this spectrum. She can say that there's helium in that star. This is useful information. All right, we're going to move on to something a little bit more complicated. Here we see illuminated water vapor. So what emission lines would we expect to see from illuminated water, and how will it look different from what we've looked at before?
So Anna says the lines we would see are from hydrogen and oxygen, and that is also repeated by Alvina and Anish. So yes.
Excellent, very, very good. So we're going to test this hypothesis now by moving the diffraction grating in front of our illuminated water vapor. Charles, would you help? Thank you. All right, excellent, very good. Hopefully you guys can all see our illuminated water vapor. Can you see the hypothesized hydrogen and oxygen lines? What looks the same as before when we were looking at just our hydrogen, and what looks different? These are important questions to ask when looking at new spectra that you haven't seen before.
Alvina says the blue and red lines are there, but there's a lot more green. Naomi says it has two bright lines in the red and light blue areas, same as hydrogen. Matthew says the red lines.
Excellent, very, very good. So we have the hydrogen lines from before, and as suggested, we see some new lines as well that might be our oxygen lines. So we have the emission spectrum, the celestial fingerprint for water. Talented and hardworking astronomers like Dr. Van Hoff can now point their telescopes at distant objects so far away that we've never been able to send a probe to them. And she can say, look, there's water, and where there's water, there could be life. This is how we look for elements and signs of life in distant stars.
All right. Thank you, Charles and Alexi, for this great demonstration of how molecules emit light. So yeah, as we have seen in the demonstration, molecules and atoms emit specific colors or wavelengths of light, and we can use this fingerprint to identify which molecules we're observing. So instead of showing which colors we observe, like this, or how we saw it in the demonstration, we like to make a graph of it, where we show for each wavelength how much light we observe. This is also
Professor,
called a spectrum.
we did end up getting a question in the chat. Naomi asked, how do you tell the difference between elements in the object of the interest and elements in the atmosphere?
Yeah, Naomi, that's a really good question. It's really difficult to do from the ground because there's so much water in the atmosphere. And I will show you in a minute the telescope that we use. It's located very high in the mountains in a very dry place in Chile, or on the mountains on Hawaii. That's why there are so many telescopes on Mauna Kea. Because you're high in a very dry place, we have as little water in the atmosphere as possible. So we have as little of this interference as possible. And most things that we see are actually coming from space. To show what light we're observing, we make this spectrum. And here we're plotting the wavelength of light, and for each wavelength, how much we see. So this is a real observation. And here we have, for example, we're observing no purple light, no light blue, but a little bit of dark blue, a bit more green, and even more red. So can anybody tell me why we're seeing these wiggles, even though there's no purple light, or there's no light blue light? Why do we still see some signal here? Does anybody have an idea? Interfered from background objects, that would be a good option, yes. So typically it's, even if there's no background object, we still see this, it's noise. And we have in any experiment that we do, there will always be some type of noise. So we'll typically never really measure nothing. There will always be a little bit of noise. So in addition to maybe effects from the atmosphere, this is always something that we'll have to take into account when we interpret our data. So unlike the demonstration where the hydrogen, helium, and water emitted visible light that we could immediately see, molecules in star and planet forming regions will emit at infrared and microwave wavelengths. So longer wavelengths than what we can see with our own eyes. But we can observe it with powerful telescopes such as JWST, which has been launched now almost 3 years ago. And ALMA, which, as I said, is one of those telescopes located high in the Chilean mountains where it's really dry and we have very little atmosphere, so it doesn't interfere as much with our observations. So JWST can detect infrared light, and since the atmosphere blocks most of the infrared light, we really have to go to space to see infrared light. And ALMA detects microwave radiation, which is mostly being transmitted by our own atmosphere. So we can do it from the ground, especially when it's in a dry place. And ALMA is a special type of telescope because all these dishes that you see in this image, they all work together as one giant 10-mile telescope. So ALMA acts as a telescope dish that's 10 miles in diameter. So we cannot physically make such a big telescope, but we can use technology to mimic such a big telescope by using many small dishes that are far apart. And the data that you will be working with in a little bit is actual real observations from ALMA. So this is how we can observe water in space. Does anybody have any more questions about that before we move on?
I actually have a question, Professor.
Yeah, of course.
Why do we want a telescope that's so large?
That is a really good question. We want to have a telescope that's so large so we can see the smallest detail as possible in our objects. And we want to look at, right, planet-forming regions. So an object the size of the solar system at light years distance, and we want to see all kind of detail in those systems. And in order to see that, we need a large telescope. And the second reason is that the longer the wavelength of light that we're looking at, the bigger the telescope we need to see the same amount of detail. So if we were looking in the optical, we need a much smaller telescope to see the same small detail as we would need. And we would need a much bigger telescope. Now we're looking at the microwave wavelengths to see the same detail. So that's why we need these giant telescopes. All right, now we can go to our main question: where does our water come from? And to start that, I want to ask you, who has heard of the term heavy water? Maybe raise your hand. And maybe, is there anybody who can tell us what is meant by heavy water? I see several hands going up. Naomi says water has a hydrogen atom with 2 neutrons instead of the usual 1. Water infused with more hydrogen is Nathan's answer. So yes, it's water with deuterium instead of hydrogen. Yes, an extra neutron. Very good. And yes, so hydrogen has a proton in the nucleus and an electron around it. And the number of protons in the nucleus determines the type of element that we have. But we can add neutrons to the nucleus without changing most of the properties. And hydrogen with an additional neutron in the nucleus is called deuterium. So if we now substitute one of the 2 hydrogens in water, so H2O, we'll get HDO. And if we do it again, we get D2O. And water with deuterium is referred to as heavy water. But why do we care about this? Why is this important? Well, it's important because it gives us a first clue as to where our water comes from. Namely, it can tell us how old our water is. So you might wonder, like, how does that work? Well, it works as follows. We know in the universe that we have about 1 deuterium atom for every 50,000 hydrogen atoms. And since hydrogen and deuterium are almost identical, they can undergo the same chemical reactions. And therefore, we expect every molecular species that contains hydrogen atoms, such as water, to have about 1 deuterium for every 50,000 hydrogens. So if we look at a lot of water molecules, we will see 1 deuterium for every 50,000 hydrogen that we see in them. This is true, except when it is really cold, less than 30 Kelvin, where 0 Kelvin is the absolute lowest temperature that we can have. And for reference, in your room right now, it's probably around 293 Kelvin. So because deuterium is slightly heavier than hydrogen due to that extra neutron, it takes a little bit of energy to break down heavy water. And when it's too cold, we don't have the energy to break it down. so we can accumulate more and more deuterium in water. Because once it's in there, we cannot take it out anymore. And this process is called deuterium enhancement. So remember, we have 1 deuterium in the universe for every 50,000 hydrogen. So what about the water in our oceans? How much deuterium do we have? We have about 1 deuterium for every 6,250 hydrogen. So about 8 times more than we have in the universe at large. So, question to you, what does this tell us about our water? Based on what we just talked about, what does it mean that we have so much more heavy water on Earth than we would expect? Okay, I see some suggestion. It was really cold at some point. Our water is pretty old. It came from somewhere cold. Yes, exactly. Our water formed in a really cold place. And when do we think it was really cold? When during Earth formation? Any ideas? Any guesses from these stages? Yes, you're all correct. In this cloud, because right, the stars will heat the material up. So when there's no stars, it will be really cold. So the amount of heavy water that we see in our oceans tells us that our water is really, really old and was formed before the sun and Earth were born. And when I learned about this, I was like, really, my mind was blown. I still think this is really incredible that we have our water formed so long ago. All right, so now we know that our water must have formed in the cloud early on, but that doesn't tell us yet how it got to Earth. And one question that we haven't answered yet is if this water formed in the cloud actually makes it into the disk and is actually present when planets are forming. So in order to determine whether there is water in a planet forming disk, we can, and this is what you will be going to do in a minute, use ALMA. So let's talk briefly about how ALMA works. So ALMA can not only measure the amount of light emitted at different wavelengths and make a spectrum, as we have seen before, but ALMA can make an image at each of these different wavelengths. So we get what we call an image cube, images different wavelengths. And remember, ALMA doesn't observe visible light, but microwave radiation. So these visible colors are just an illustration that it observes different wavelengths. But it also means that in order to visualize the images that ALMA takes, we have to assign colors ourselves because we cannot see microwave radiation with our eyes. And what we typically do is we do not use 1 color per wavelength, as in this example, and we have it visible, but we typically use different colors to indicate how much radiation we see at different locations. What does that mean? Well, this is an example of an image of a planet-forming disk obtained with ALMA, in which we think planets are maybe forming right now in these dark rings. So I think this is really exciting that we're trying to figure out. But in this image, we use brighter colors to indicate more emission and darker colors for less emission. So there's more emission light coming from the inner region and there's less coming from the outer region and from these rings. So I think it's pretty intuitive, but the color is not real. So how can you use ALMA? So if I, as an astronomer, want to use ALMA, I have to write a proposal arguing why I want to do the project that I want to do. And we can do that once per year. And then the most exciting projects will be selected because there's unfortunately not enough time in the year to do them all. And getting ALMA data and using ALMA is actually pretty challenging because about 1 in 8 projects that get proposed gets selected. So it's really challenging. But the good thing is that after a year, observations that have been taken, they become publicly available in an online database and anybody can access them. So that's what we're going to do. And for this, we're going to go into breakout rooms and I'll stay in the main room. So you can always come back there. And then after about 15 minutes, we'll come back here again and talk a little bit more about where the water comes from. So Thomas, I'll give it to you to make the breakout rooms. And then I'll see you back in a minute.
Zoom tabs out of the way. So we went to this ALMA website, which is linked in the project description. We went to this data tab and then this archive tab, which led us to this screen. And then we pasted our project code into here, which the project code is also listed here to copy and paste. That automatically brought us to this location in the sky. And then we clicked on this explore and download B1-C option, which brought up a large number of observations. And we wanted to find the observation that had this image and matched this name and this frequency. So this SPW2 source. And so the way I found it was just by looking at the different observations that had images attached to it. And I found one with the same like little graph here at the bottom, which ends up being this one. And we can see the name and frequency match. I'll switch it over to Roy now. Looks like Mariana, Anika, and Naomi found it. Was everyone else able to find the observation okay?
Alrighty then. So what you want to do next is click on this little cube icon right here with the little semicircle around it. Click open in new tab up in the corner here. Your screen should look like this right now. Click on this little zoom in button with the little plus sign, the magnifying glass. You want to click on that 5 times. So 1, 2, 3, 4, 5. Click on this ellipse icon right here. Click and drag to form an ellipse. You can click and drag to move it around or change the dimensions of the ellipse as well. Basically, what we're trying to do is highlight the region we want to look at and take a spectrum of. So you can see my icon. This is the button you want to click on, this spectral profiler. And when you click on that, you get a menu that looks like this. You get this plot. Next is basically where it says statistic. You want to click on where it says mean and then hit flux density. If you click and drag the plot away from the image to reveal it, you should see that there's a very bright point of emissions. Click and drag and move your ellipse over this bright point.
Also, Roy, with the pinning the graph thing, I think what you have to do is on the little pin icon in the upper right, you have to click and then drag that into the boxes.
Oh, okay. Yeah,
and then you can exit out of like the Y profile region 1 and the X profile since we aren't using that, and then that will allow us to just pin the Z profile that we're using.
Okay, there we go. Yeah, thank you.
Yeah, of course.
So basically what you want to do is click on this push pin icon, and then there's a little highlighted region you'll see on the side. If you let go of your mouse, it'll just put the plot right next to the image. So you'll have it like this. What you want to do from here is go to this icon, the special or the spectral line query widget, and then you click on this. Make sure our units are correct. This is where it says megahertz right here. We want to change it to gigahertz. So you click on the drop-down menu, you press this. Now, what you want to do from here is set a range. So we want to look on our plot to see what frequencies it covers. So you can see maybe it's around 225. So we can say 225 gigahertz to 226. So we'll type that in. And the velocity we want to put is 6 kilometers per second.
So why do you say 6 kilometers per second? Where does that come from?
It's basically the velocity of the source that we're observing. So the protoplanetary disk has a relative velocity or velocity relative to Earth of 6 kilometers per second, which is what the scientists were able to measure. Objects moving farther away from you appear to be redder, and objects moving closer to you appear to be bluer. So we have to take velocity into account when taking spectroscopic measurements because it can affect the color or the wavelengths or frequencies of light that we see. and that can affect our measurements. So that's why we have to type in a velocity value so it knows how to account for that. So once we're done with that, we hit query. And we get a bunch of molecules in this spectrum. But what we're particularly interested in is heavy water. From here is under chemical name. We type water with a capital W. Then you hit enter. And you want to click on this checkbox here where it says HDO. So, and then you could see this line just appeared. And this is the peak frequency for water. So
how did it go? Did you all find water in the disk? Yeah, I see some thumbs up going. Good. Then let's go to the last part real quickly. So now that we know that there is water in disks and is likely also in the disk from which Earth formed, how did it got onto Earth? So the last step is still missing. And we can get a clue if you look at the different planets in our own solar system. So what do you notice when you look at the different planets? Are there any trends that you're seeing that stand out to you? You probably notice that we have these giant planets in the outer solar system, so the gas giants and the ice giants that we call them. And then in the inner solar system, we have these tiny rocky planets like Earth. So we can understand why we have an architecture in the solar system like this by looking more closely at the planet-forming disk. So remember, we have our newborn star in the center that's heating the gas and the dust in the disk, making it closest to the star, the warmest. And as we go further away from the star, the temperature will go down. And at some point, it will get so cold that the water cannot stay in the gas anymore, but instead it will form an ice mantle on the dust grains. And this phase transition is called deposition. And this is the same thing that happens when you see the grass being white on a very cold morning, but it hadn't snowed. This is the same process, water going from the gas to the solid phase. And so that means that in this disk, we have dust, gas, but also ice. And the location where we have the transition from water gas to water ice, we call that the snow line or the ice line. So now remembering that planets form from dust grains, as we saw before going into the breakout room, so where do you now expect that a planet like Earth would form in the disk? Inside or outside the snow line? Yes, indeed, inside, right? There we have only bare rocky grains and we form a dry rocky planet. Well, if we form a planet in the outer disk with icy grains, we might form a larger planet or an ice giant. So the planets in the inner solar system are rocky because they formed from dry dust grains and rock. And this gives us the first possible theory that can explain why there is a little bit of water on Earth. And that's a theory that predicts that this snow line moved closer to the star while Earth was forming. So like we just said, Earth started forming inside the snow line from dry rocks, but by the time Earth was almost fully formed, the snow line had moved inward far enough that the last material to be accreted onto Earth was actually icy and brought some water to Earth. So this is one theory. A second theory is that the rocks that formed Earth were not completely dry. Even though they were inside the snow line, they didn't have any ice. And here you can see an electron microscope image of an interplanetary dust particle that was collected by a NASA aircraft. And you can see that it's very porous. There are all these cavities and holes in it. So one theory says that maybe there was some water present in these pores, and that's why there was some water brought to Earth when it formed. So the grains, even though they were dry inside the snow line, they had some water inside of them. So that's another theory. And finally, we can get a clue if we look at the water content in meteorites. And many of you already mentioned meteorites in the beginning when Mariana asked about where the water came from. So when we measure the amount of water in meteorites, we see that the meteorites that originated closest to the sun have the least amount of water, and the meteorites that were formed furthest away from the sun have the most amount of water. So knowing that meteorites are basically leftover remnants of material that didn't make it into planets, we could expect that the Earth should have the same amount of water as meteorites that originated in the same region. So we measured that, and it turns out that this is not the case, to our surprise. So Earth is about equally wet as meteorites coming from the asteroid belt between Mars and Jupiter. So this led to the third theory that maybe some of the water comes from bodies out from the outer part of the solar system, like asteroids or comets, which many of you already mentioned in the beginning. So that was really good. But with what we all talked about today, can you now think of a way that we can verify whether comets, the water on comets, is the same as we have on Earth? So what can we measure to determine if the comets really brought water to Earth? Spectral lines, yes. So what spectral lines would you do? What would you look at in particular? The deuterium content, yes. So yes, we can compare the deuterium content in cometary ice to that what we have on water. And that's what we did. And we find that there's about 1 or more deuterium per 6,250 hydrogen atoms in cometary ices. So we have the same amount of heavy water compared to normal water in comets, or even more than we have in Earth. So this suggests that, yes, indeed, some comets might have been responsible for bringing some of the water to Earth that we see today. So to summarize, we did a lot today. We have seen that our water is very old and formed in the cloud before the sun and the Earth formed itself. You've seen for yourself that this water actually is present in the disks where planets are forming. And we've talked about how Earth formed in the disk in the warm region without water ice, and that there is at least 3 theories that may explain why water came to Earth. So like I said in the beginning, we don't know yet if there's one theory that's the most correct, or whether they all played a role and played a part. And maybe there's even more mechanisms that I haven't talked about today. So while we know a little bit about where our water came from, we still have a lot to learn about how our own planet formed. And maybe someday some of you will contribute to this as well. So with this, I would like to thank you very much for your attention and your great participation. And I'm going to hand it back over to Mariana for the last part.
I guess, so I have a quick question just so we can get some context on the planet forming region we looked at. So do you know how far away from Earth it is?
Yeah, so this is at about 300 parsecs. So it's one of the closer regions. It's in Perseus, so it's in the Perseus star forming region. Yeah, I think it's about 1,000 light years away, if that says probably more. So yeah, the closest ones that we have are Taurus, which is about 500 light years. So these are a little bit further away, but still that we can see them with ALMA. Yeah.
Cool. So that's also something else I think is pretty cool, that we can see something that's so far away and see what kind of compounds are there.
Yeah.
Thank you very much for coming today to learn about chemistry in space. Thank you to Dr. Van Hoff for giving a really interesting presentation, and to all our TAs for helping with the breakout room. So thank you for attending Saturday Morning Astrophysics at Purdue. Please stay tuned for the next events coming up soon. And I hope you guys all have a great rest of your weekend and happy holidays. Thank you.